Hello everyone, my name is Carolyn Ugarte.
And I'm Odette Tannous. We are super excited to present you a remarkable innovation in the field of chemical biology called the copper-free click chemistry for dynamic in vivo imaging. Carolyn Bertozzi, alongside with the Morton Medal and Barry Sharpless, won the Nobel Prize for pioneering the click and bioorthogonal chemistry. Click chemistry often is compared to snapping Lego bricks together. It's fast, clean, and efficient even in water. Of course, this revolutionary work was led by the Nobel laureate Carolyn Bertozzi, and that addresses key challenges in biomolecular imaging.
She received the 2022 Nobel Prize in Chemistry for her contribution to bioorthogonal chemistry, a field she starts. This paper represents a cornerstone of her work, addressing the need for biocompatible reactions to study biomolecular dynamics in living systems. It's essential to understand the following key concepts. The first one is glycan. A glycan is a polysaccharide or sugar chain that plays a crucial role in cellular communication and recognition. Lipids. These are organic compounds, including fatty acids and their derivatives, and they are essential components of cell membranes and energy storage. Then, GFP, green fluorescent protein. It's a protein commonly used as a marker in imaging to visualize biological processes in real time. And finally, these two important reactions will be explained in detail in the next slides, but CuAAC, copper catalyzed acid alkene cycloaddition, is a traditional click chemistry method that requires copper catalysis but is toxic in live cell environments. And finally, the SPAAC, strain-promoted acid alkene cycloaddition, it's a copper-free click chemistry approach that uses ring strain to drive reactions, making it biocompatible and suitable for live cell studies, as we will see. Then, let's start talking about the challenges in biomolecular imaging.
So while proteins molecules can be tagged with GFP techniques for imaging, non-protein molecules like glycans and lipids have like a unique challenge. Existing methods like copper catalyzed acid alkyne cycloaddition called CuAAC involve copper as a catalyst, which is cytotoxic, making them unsuitable for living cell applications.
Because of this limitation, it was found the strain-promoted acid alkyne cycloaddition, SPAAC, a copper-free alternative. This uses a strain in cyclic alkynes to drive acid alkene cycloadditions, enabling safe and efficient labeling in living systems. In this picture, we can see the bioorthogonal chemical reporter strategy. It may offer an avenue for labeling and visualizing biomolecules in vivo without the requirement of genetic manipulation. In this approach, the cell metabolic machinery is used to install a bioorthogonal functional group into target biomolecules, which is then covalently labeled in a second step with a proof. The acid is the most widely used chemical reporter because of its small size, its metabolic stability, and the lack of reactivity with natural biofunctionality.
Cyclooctines, with their inherent ring strain, can rapidly react with acids. This innovation bypasses the need of cytotoxic copper catalysis. So the chemistry behind the SPAAC combines two key principles. The first one, that the ring strain of the cyclooctines accelerates the reaction. Second one, that the fluorine substituents stabilize the transition states, increasing the reactivity.
To increase the sensitivity of the cyclooctanes for acid detection, the group combined two powerful rate-enhancing features, ring and strain and electron withdrawing groups, with the design of copper-free click reagent marked as 1 in figures 3 and 4. They choose the difluoromethylene moiety as an electron withdrawing group because of its synthetic accessibility and its inertness in biological systems. Importantly, this group doesn't create an electrophilic mycoacceptor capable of alkylation biological nucleophiles as would a conjugated substituent such a carbonyl group. The synthetic route for defluorogenated cyclooctane is shown in figure 4. The design enhances reactivity without introducing toxicity.
So, kinetic analysis revealed that the DIFO reacts 63 times faster than the previous strain promoted cycloadditions. That is a big improvement for live cell applications.
To compare the efficiency of the copper-free click reaction using defluorogenated cyclooctane with copper-catalyzed click chemistry, researchers conduced experiments under pseudo first-order conditions. This approach used an acid-level protein as the limiting reagent. Derivatives of DIFO and terminal alkene conjugated to the fluorescent dye Alexa Fluor 488 were reacted with the recombinant dihydrofolate reductase proteins that include an unnatural acido-homoalanine amino acid. This setup is illustrated in figure 5. As a result, both copper-free and copper-catalyzed reaction reach saturation within the first hour. Defluorogenated cyclooctane demonstrated sensitivity comparable to copper-catalyzed click chemistry, but with the advantage of being biocompatible and non-toxic. This confirmed the high selectivity of both methods. To evaluate the effectiveness of DIFO in live cell labeling, the group compared it to other acid-specific reagents. In this experiment, Ugarte cells containing acidocyanic acid residues on their surface glycans were labeled with biotinylated derivatives of DIFO, a combination of DIFO with biotine, a phosphine reagent, and a non-fluorinated cyclooctane. The results quantified using flow cytometry show that DIFO combined with biotine outperformed the other reagents by a factor of 20. Remarkably, DIFO combined with biotine labeling was effective even at nanomolar concentration. Additionally, no cellular toxicity was observed at any concentration, as confirmed by morphology analysis and propidium iodide staining. This is an important result because DIFO combines the high sensitivity of copper-catalyzed click chemistry with the biocompatibility of the Staudinger ligation and strain-promoted cycloaddition, making it an ideal reagent for bioorthogonal applications. As we mentioned before, the previous bioorthogonal labeling methods were limited to static imaging, which failed to capture the dynamic behavior of glycans and other post-translational modifications. Then, to overcome this, researchers used copper-free click chemistry with DIFO 488 to achieve real-time imaging of glycan dynamics in living cells. Then, let's talk about the experimental setup for dynamic imaging of glycans in living cells. First, the cell mother. Researchers used Chinese hamster ovary cells, that it's a widely used cell line for studying glycosylation. These cells were metabolically labeled with acidocyanic acid, which incorporates acid groups into their cell surface glycans. For the labeling process, the cells were incubated with DIFO 488, that is a fluorescently labeled cyclooctane proof at varying concentration and time intervals. The DIFO-488 reacts specifically with the acid groups on modified glycans via strength-promoted acid alkene cycloaddition, the SPAAC reaction, enabling rapid and selective labeling. For the fluorescence detection, labeling was analyzed using fluorescent microscopy to visualize glycans on the cell surface. The key goal was to detect glycans on a minute time scale while ensuring minimal background fluorescence. Then, for the time-lapse imaging, after the initial labeling, time-lapse microscopy was used to monitor glycan trafficking over the course of 1 hour. Localization of the fluorescent signal of endosomes and Golgi compartments provides insights into glycan internalization and processing.
DIFO-488 allowed researchers to visualize glycan trafficking in real time. And within minutes, fluorescently labeled glycans was observed moving to intercellular compartments.
After incubating the cells with DIFO-488, fluorescent labeling was observed within 1 minute. This quick reaction demonstrated the high efficiency of copper-free click chemistry using DIFO-based reagents. Negligible background fluorescence ensured that the labeling was specific to acid-modified glycans, validating the selectivity of the method. We can see this from figure A to H. Then, for the time-lapse imaging, the labeled cell surface glycans were tracked over time using fluorescent microscopy. Within the first 30 minutes, fluorescent signal shows glycans being internalized into the cell. Fluorescence localized in endosome and Golgi compartments, confirming the recycling and enzymatic process of glycans. These observations were supposed by localization with markers for transferrin uptake for the endosomes and Golgi apparatus. And these are the figures I to N. Then, for the kinetics of the internalization, the fluorescence intensity in intracellular compartments increased rapidly within 30 minutes and then plateaued. Analysis indicated that a half-life of approximately 15 minutes for the internalization of a subset is enough. This finding provides quantitative insight into glycan trafficking dynamics, which was previously difficult to achieve with other methods. But what is the significance? These results demonstrate the capability of copper-free click chemistry to track fast biochemical processes with high precision and minimal interference. This method enables real-time visualization of complex glycal behavior, highlighting its value in studying cellular dynamics. Now let's talk about the applications and broader impact. This technique is transforming glycobiology by enabling real-time imaging of glycosylation and other post-translational modification in living systems. Some research applications are studying glycosylation dynamics, enzyme activities, and drug interactions. And some industrial applications can be related with the cancer diagnostics and target therapies.
So, in medicine, copper-free click chemistry can improve diagnostics and therapies, such as creating a safer or designing a safer imaging probes for cancer detections. In conclusion, copper-free click chemistry represents a leap forward bioorthogonal chemistry, overcoming the toxicity of previous methods while maintaining efficiency.
Looking ahead, expanding this technology to other biomolecules could further enhance our understanding of cellular processes and lead to new therapeutic strategies.
Now, to close, we're gonna leave you with a reflection from Carolyn Bertozzi. When you design tools, that interface with biology. You open the door to solving problems that weren't solvable before.